Good day and welcome to today's CAVA webinar from TECHNIA. You're very welcome that you've joined that webinar. So I've started to show my screen and I will start with a short CAVA presentation just about the organizational task. Yeah, we'll have this webinar via GoToWebinar. You can also suggest questions or feedback via the chat option. And yeah, you can request the slides after the webinar. And for your information, the session will be recorded. And at the end of the session, I will stop the recording and we can have a question and answer session. So what will you see today? Today we're going to talk about CAVA radius, safety radius analysis on the interior and the exterior of automotive parts. This is important since it hinders during any accident, it will ensure that the occupant or a pedestrian will not be hurt as more than actually, it will help avoid critical injuries. So we will see actually mainly three topics and a live demo. We will talk about the requirements for the safety radius checks on the dashboard, like the head impact zone and the exclusion areas. We'll show how to analyze the reachable zones with the help of the test sphere or the test pendulum. And we will show how to measure the height of projecting elements and how to evaluate exception rules in the R21 with respect to these projecting elements. If time permits, I will still talk about similar actions on the exterior of the part, like the bumper zones and the grills. So just a few words on CAVA in general. So CAVA is TECHNIA's solution for legal compliance in car design area. CAVA itself is an abbreviation for CATIA V5 Automotive Extensions for the Vehicle Architecture. And actually the product is designed to validate the compliance of your product designs to the legal standards or other requirements. And CAVA here brings a set of standards and guidelines as features within the CAD system, and you can apply that directly to your design in the CAD system. So major benefits of CAVA: you can organize your car project and have parametrical input for the car in the so-called CAVA base data. If you apply CAVA on your digital model, of course, you have less need for physical prototypes or can avoid them overall. And CAVA is designed to be applicable in all design phases of the design process. So you can start right on when you have just conceptual information, like parametrical input, like width of the car, position of the wheels, other elements, and you can already start getting information from CAVA about allowed building spaces or zones to avoid some critical elements. Yeah, CAVA is actually a set of products. It handles about the packaging process in the vehicle architecture, OVA product, can handle about direct and indirect vision. And one module we're talking about today is about safety of occupants and pedestrians, especially the safety radius checks. Just to complete it, CAVA also has some functionality for wiper analysis, kinematic analysis. Mannequin analyzing allows you to analyze the positioning of a mannequin in the car and determine leg room and other measurements like the heel reference point or pedal reference points. Okay, in general, CAVA is deeply integrated into CATIA. Whenever you start CAVA, you will see the CAVA workbench with the toolbars that are required in the specific modules you're applying. And whenever you create a CAVA feature, it will be shown in the feature tree and it will react as a regular CATIA feature. That means all inputs and outputs are accessible. So if you change any input parameter or input geometry, the CAVA feature will notify you that it requires update, or it will update automatically as per your setting. Okay, that's about CAVA in general. Now I'd like to focus on today's theme, like legal requirements for the minimum radius, like for example in the ECE R21. So in this use case, you are facing the issue to check your design if there's any radius which is larger than the required R-min, minimum required area, in the zone you're currently working on. And so how CAVA will support you in doing this analysis. And here we have different variants of the functions aimed towards the different regulation specifications. For example, for the interior, in the regulation, there are mainly four different areas. One is the forward compartment of the interior parts of the passenger compartment in the front, before the H point, and excluding the side doors. So this is mainly aimed for the instrument panel. And here special rules like the reference zone or exclusion zones apply. Then there's 5.2, which are the remaining interior parts on the front, this time below the low-level instrument panel. And this is a special function for that, the so-called knee-form analysis function. Other interior fittings of the passenger compartment, also behind the driver's H point, like the side doors, any other panels, and needs to comply to the regulation 5.3. And last but not least, there's the regulation of the roof in 5.4. So each of these zones or areas in these zones have a different radius requirement. And one of the challenges is to define in which zones do these elements you're analyzing fit. And you have to find if in this zone you're violating the regulations. Luckily, CAVA can assist you here. You see on the next slide. First here you will see how, for example, the head impact zone or the reference zone is determined on a physical prototype. So in a physical prototype, it is described in the definition of the reference zone you will find in section 2.3 and 2.4 of ECR 21, and the method of determination of the head impact zone in the Annex 1. So basically this describes a pendulum shape, a pendulum fixed to the H point or also to a moved H point, and you can vary the pendulum in length, and by moving the pendulum towards the dashboard, and you trace the contact points, you will get the front and rear boundary of the head impact zone. Furthermore, there are defined exclusion zones, for example, like the exclusion zone around the steering wheel, which requires an offset the steering wheel and a certain offset to the steering wheel and the lower edge of the steering wheel. So, and the remaining part of the head impact zone minus the exclusion zones is finally the reference zone, where you have to comply to special regulations like the minimum required radius of 2.5 millimeters in some cases. How can CAVA help you here? So CAVA has the function to, of course, do the radius analysis, but for the challenging task of determining the reference zone, CAVA can visualize the individual boundaries like the level of instrument panel, the exclusion zone around the head impact and around the steering wheel, and of course the pendulum zone with the moved with a long and short pendulum at the H point, and in case of a sliding seat also a moved H point. So then CAVA will also determine if this area of the dashboard will be able to get into contact with the sphere at the top of the pendulum, because many areas are probably not contactable due to cavities or concavities. And so CAVA can, during the determination of the reachability, it will consider the explicit movement of the pendulum. So it will move down in a specific angle, and CAVA will determine the first contact points where the movement will stop. Finally, as a result, you will get some approximate boundaries of the head reference zones, and all analyzed points within this zone are marked in the respective colors, if they are reachable, if they are critical above the minimum required radius for this reference zone or not. This can be applied to not only to the driver, it can also be applied to the co-driver or any other seating position in the car. In the two pictures you see on the left hand the reference zone, reachable reference zone for the driver, and on the right hand side you see it for the co-driver. Visualized, you see also some pendulums for individually selected points, which you can do in a so-called interactive check. Yeah, in addition to the reference zone, which has specific areas, you can of course also visualize the complete selected dashboard, and you get a color-coded feedback, a separate color-coded feedback for the requirements outside of the reference zone. So for each of during interactive analysis, you can select any of the points. You can inquire the curvature radius at this point. You can also create a cross-section of how the sphere will approach this section. And you have a special 2D section viewer, which you can use to create screenshots and for any reports. So you can document any critical situations you might find and want to document to be changed. So for now, we have talked about the reference zone, which is above the level of instrument panel. Also in ECR 21, we have the so-called, the section 5.2, where the contact is not calculated with a sphere and a pendulum, but with a so-called knee-form shape. And CAVA is also able to calculate the reachable points in the lower part of the compartment, specifically with the knee-form shape and considering also the movement of the knee-form shape as it is written in the ECR 21 regulation. But important to know is that for many of the parts you analyze, you will find critical elements. Rather, it might be in gaps or in some imprints on the dashboard, like the airbag sign, or also, of course, some of your switches and knobs may stand out, also vents, and they may have actually a radius smaller than the required 2.5 millimeters. For that, in the regulations, there are some exception rules in case these elements do not project out of the dashboard by more than a certain height. For example, switches that, anything that is below, does not project more than 3.2 millimeters, does not need to have the 2.5 millimeter radius, but it has to be blunted, means have a radius of at least 0.5 millimeters. Also for grills are regulations where it's helpful to be able to measure gap sizes and other elements. So the ECR 21 documents two methods of determining the projecting height of elements. One is the projection with a measurement gauge you see on the right-hand side lower picture, which is designed for small knobs or switches that fit with a diameter of less than 50 millimeters. In this case, you can have this measurement gauge and put it on the dashboard, and you have a movable cylinder inside where you can measure the projecting height above that. So this method is also present in CAVA as the function for the projection measurement device, and it simulates this measurement. But in most cases, or very often, an element which is projecting will not fit into this element. And in this case, there's the method of measuring projections according to Annex 6, where you have to create cross sections. And with the this picture here shows a picture of how that is done. You create cross sections, and you have to provide circles or spheres in touch with the projecting element. And between the touch points, you determine the highest point measured on the level line between the two touching spheres. So also this method is now present in CAVA. It's called projection measurement in sections, and I will now show you how to apply that on a few slides, or what it is for. So projection measurement in sections is a very flexible function to determine several aspects of projecting heights. It can be applied on the exterior and the interior, and it's based on creation of a set of sections or a set of sections with a given offset along and orthogonal to a curve. It can be used, for example, to measure projections along gaps, like you have this upper left picture when you have a hood and another part of the outer geometry where there is a gap in between and there might not be aligned exactly, and you can use this measurement to determine a so-called projection value of one part over the other. Then for the interior, you have more the classical case that you see in the lower end, where you either have a switch or knob which fits into the projection measurement device. In case not, like for the airbag sign or the other longitudinal element that was not fitting into the measurement device, you can use the projection measurement in sections along a curve, and CAVA will determine a lot of sections, and display will show you the critical values here. In general, for projection measurement, you have to decide between two measurement options. One is a two-sided option, and one is a one-sided option. Two-sided option, as also the picture in ECE R21 and 26 will show, will require that the sphere on the geometry of the dashboard, or the so-called rolling geometry, can be approached from both sides in the section. This is not always the case. In these cases, you can also use a one-sided value where you only approach the sphere or circle from one side to the touch geometry, and then you measure the height based on the tangential level of the touch point on the rolling geometry up to the highest point on the touch geometry. So CAVA provides both options in the same function. It's providing it for ECR21 and ECR26, whatever you would need. Yeah, so the result of the projection measurement in sections is the sections itself, but for each section also a measurement value. And CAVA here provides a markup capability, so you can import. If you're doing a projection measurement in sections, you can select a reference feature from the radial analysis, which has critical points or violating points. And with the help of this tool, you can assess the violated points if they are within the limits. And if the designer thinks or is convinced with the help of the measurement that here an exception of the regulation can be applied, you can mark these points as accepted and store these accepted regulation results in for a documentation purpose that this situation has been analyzed and deemed as okay due to the exception rules in the regulations. Okay, before I go to the live demo on CAVA v5, I also want to point out that CAVA functionality is also available in in CATIA V6 and the 3D Experience platform. So whatever I'm showing now in the CAVA CATIA V5, you will also be able to experience in the 3D Experience platform with the same functionality level. Okay, I will now go to the live system and show you some of the application live. Okay, you see here now an example of a dashboard of a car with also some environment like the windshield or the door. You also see some knobs, switches, vents, and a GPS device, as you have it on in current dashboards. And so here you can already imagine that determining the head impact zone is not easy due to the projecting elements like the LCD screen or these vents. So, but of course, CAVA can assist you here and is capable of calculating this reference zone and the radius. I will show it on here for the co-driver. To determine it, you will start the CAVA interior function, CAVA interior minimum radius. Okay, so you would see the CAVA radius user interface, which looks, yeah, it's very capable function. So you have to orient yourself. On one hand, you can select the CAVA base data. CAVA base data contain, for example, all seating positions of a car, so which is important for the pendulum check of the ECR21. Therefore, I have to select the CAVA base data. As a standard, there are ECR21 and FMVSS 201 available. Today we'll focus on ECR21. FMVSS 201 is also possible, and it's just a slightly variant of it. So after that, you can decide what kind of calculation you'd like to do. For example, do you want to create the head impact zone or just the head impact zone? For my demonstration, I would like to create the head impact zone. I would like to do the radius check as well in parallel. And I want to consider the level of instrument panel and also the excluded area. So these are options because in some cases you might want to consider the complete dashboard without the exception zones, or you do not have the required steering wheel information, so you can do also work without that. So in the lower panel, you also see parameters like the definition, the minimum required radius for the head impact zone, for the remaining interior and for the roof, and also some values for the pendulum. These are points, values coming directly from the standard ECR21. We have some additional options for the head impact zone. For example, if you would like to see the complete pendulum range or only the reachable areas, which I choose here. And you have other performance options. For this demo purpose, I'd like to switch some options to have a quicker performance. And yeah, on the top, you see several tabs where you can add other inputs, like for the seat. You can here switch which kind of seat you are analyzing. So I'd like to do the passenger side. And I have a sliding seat. And based on these inputs, I can now add my geometry that I'd like to analyze. This is done in the lower area of the user interface. So you start by filling this list of geometrical elements. So you're selecting, for example, the upper dashboard geometry, and you assign some properties to it, like What kind of geometry is it? It is, for example, instrument panel, which is, then it's used for the level of instrument panel. If I do not assign anything, it's just regular interior geometry. But the dashboard I'd like to set as instrument panel. And I also have to take care if I use surface geometry about the orientation. There's an indication error, and I will switch the orientation towards the side where the sphere will approach the geometry. If I set the parameters, I will add it to the list with a plus sign. So I will also add other geometry like the lower dashboard. We'll also add a GPS element display. Other elements, add ventilations. Let this knob, this element, and this element. In addition, I have to, since I have selected to use the exclusion area, I also need to define a steering wheel. And I have to classify that as a steering wheel. I also want to include the door, but I do not want to analyze the door. I just want to act it as an obstruction because it hinders the sphere in contacting some parts on the dashboard. Do this, I can select the door, which is just some kind of CGR geometry. And since it has no geometry anyway, I can mark it as an obstruction only. Same this part of the door. And then I'm actually have done all my selection of the elements. I have classified them as I would like. Then I can have another preview if I have the orientation of all elements correct. There's a so-called surface orientation. Okay, I forgot to add this element to the list, but now I have it. So there's this preview window about the CAVA, the surface orientation, which you can separately rotate your element. And to analyze the orientation of the surfaces, you orient it that all relevant surfaces are visible, and you click on the question mark. After that, you get a feedback if elements have the same color, they are all oriented consistently. Otherwise, you would be able to switch orientation here with these orientation arrows. But now I'm fine to start. And I will now quickly run it in a lower resolution, just not to waste too much time. And let's start it. So CAVA is now calculating the required elements, like right now it's a head impact zone. So now it has calculated a result where you see color-coded areas and also the areas of the head impact on the dashboard. So it's relatively coarse, therefore you've seen how to do it. Usually you would use a higher precision, which you can also use by the slider or also set parametrically. And I have recalculated this with a, higher resolution, which will take usually, in this case, 3 minutes. But I will use this for further explanations. So to explain the colors of the feedback, you can open the user interface and you see in the visualization tab the different colors you have selected. So red means is a color below the required minimum radius and needs your attention. Green means this is a point which is reachable by the test sphere, but the radius is okay. It's above the required radius. And black indicates that this point will not be able to come in touch with the sphere because it cannot be reached by the sphere. So important is you can show the color feedback just for the head impact zone or the complete one. So I'd like to just see the head impact zone. I'm switching off curvature, and then you will see color-coded feedback other than black only in the area of the head impact zone. So this is the area where the special rules for head impact zone apply. All other elements outside of the head impact zones, and the radius of 3.2 millimeter is the relevant radius. So if you'd like to analyze a specific point, you would go to the interactive check. You can press start. Then it will start the interactive analysis. And if it's active, you can select your critical points and inquire the radius and visualize, for example, the pendulum or section at a specific point. Here, these points are marked as critical. Let's see. Okay, so I selected this analysis. You will see how the sphere gets into contact. So it's a reachable point. And you see also the point of measurement and the curvature radius, which is 3 millimeters. Required would be 3.2 millimeters. So in this case, you would need to get active here, either change the radius of this round to a value larger than 3.2 millimeters, or add some, do some other measures that this would not come into contact with the sphere. For example, by adding a center knob, which would hinder the sphere in contacting these elements. So whenever you select a point within the reference zone, CAVA will not only display the sphere, but it will also show which pendulum size and from which point this point would be in contact. So in this case, the pendulum length would be 752 millimeters. For all other points where this pendulum hinge is not shown, they are outside of the pendulum range because the value of the pendulum is not in the given range between 736 and 840 millimeters as defined in ECR 26. Okay, so now as a result of your analysis, you have several critical points. For example, on this sign here for the airbag imprint, and you cannot change this often because they are very small elements. Now you have to check, or the designer has to check, if some of the exception rules will apply, and I will show you how to do that. First, I'm hiding my analysis, and I would like to know if this element is projecting out of the dashboard by more than the allowed 3.2 millimeters. Since it's a concave area in the dashboard, it's not so easy to find, or in general, not easy to find the highest point. So you can use the CAVA projection measurement tool to use that. So the projection measurement tool, as I mentioned in my slide presentation, can be applied to ECR 26 or ECR 21. For the interior, I'm switching to ECR 21. Difference is only the circle radius. For the exterior, you have 50 millimeters. For the interior, it's 85.2 millimeters. Next, you have to select a curve along which the sections are created. So sections are always created orthogonal to the curve by a given distance of the offset you specify here. For now, I'm using 5 millimeters. Then you have to decide if you have looking at a one circle touch or a two circle touch situation. So as a remembrance, you can here also look. This is the one-sided touch situation where you only can approach the sphere from one side. But in our case, we would like to use the two circle touch because it really can approach the element from both sides. Then as geometry, you have to select the rolling geometry where the sphere approaches the projecting element. So I'm using here the dashboard geometry, and as the touch geometry, I'm using the element of the airbag sign. That's basic inputs you need. You can also, since it creates sections to the complete geometry, you can limit that to a certain length. For example, the rolling geometry, the dashboard is very large. I don't need sections to the whole element, so I can actually, I'm restricting it to a length of 200 millimeters. It's not required for the touching element, it's small anyway. Okay, having set these elements, I can press the apply button. CAVA will calculate the sections. By default, it will show all sections. The result values, you can manage sections and visibility in the results tab. For example, you see the element with the highest value. And I have the right mouse button. I can manage the show to show only the critical element. So you see the two approaching spheres, the touch points and the highest point in between. We also have a section viewer, which is, you can inspect it in the critical view. So you see the elements, the white circles, which are the approaching circles, and the red circle is the circle in the highest position between that point. And the measurement we take is 6.16 millimeters above the connection line of the center point of the two white circles, or the so-called lift of the sphere. This is the relevant value. So in this case, it's above 3.2 millimeters. Actually, it's a bit exaggerated. It should not. So that would be, you need to have to flatten it up or put it down. So this value would not be below the allowed limit. But to show you how this can be applied to the previous analysis, I'll show you how to do that. So in the violated points tab, this list is currently empty, but you can fill it with the previous analysis we had done on the minimum radius requirement. Well, by clicking on this element, CAVA will import the critical points, which had been found here. And they are visualized currently in this red color. Now, based on judgment by the designer, who says if I say the height acceptance, for example, I change the limit here to 6 millimeters. And I have the option to accept all which are below this height limit, which can be set by the user. And if I press then accept, the accept value, the imported critical points will be evaluated and marked with an attribute that they are accepted exceptions. So you see it in the change of color and also in the violated point lists. You can sort by the status and you see that some of the elements are critical elements are now have a status OK due to projection management in section. So with this approach, you are able to document your analysis and your measurement methods with the stored CAVA feature. So it's also possible to stagger this. So you can now add another projection measurement in section feature and reference the previous projection measurement in section feature. So you can, one after the other, reduce the number of violated points to accepted violated points until you are satisfied with your analysis and documentation. Or redo the analysis if you change any of your input parameters. For other elements like this regular knob, it's also possible to use the projection measurement device function, which will simulate the measurement gauge. So in this case, you have to select as well the car interior and also the button geometry, and CAVA will check if the element fits into the measurement gauge and position the measurement gauge in an orientation that the maximum projecting value is calculated. In this case, it's 11.8 millimeters. Usually it should be below 9.5 millimeters. And you see here an exclamation mark because it's below the expected value. Okay, this was my presentation about the interior on the dashboard. I'd like to also show you a quick reference to the CAVA safety radius for the exterior according to ECR 26. In this case, we have similar exception zones like for the bumper on the lower line, you have the bumper reference line or the bumper line, which is an area of contact with a cone of 15-degree side angle. All points below this line will not need to be changed, need to be checked of the minimum required radius. And we also have what we call the so-called bumper zone. The bumper zone is an area simulating just the entry, the first 20 millimeters of entry of the car, where different values may apply in different countries or locations. And if you activate this zone, everything in the, which would be in this volume, visualized volume, or if any point, if you project it on the road level, falls into this zone, which is the bumper zone, this will be checked for a different radius than the remaining bumper if you activate the bumper zone. So there are similar zones on the exterior. Don't want to go into further details for that presentation, but there's a similar concept, and you can apply the same concepts I've shown on the interior for projection measurement, also for the exterior in certain gaps or other projecting areas. Okay, with that, I'd like to end the live presentation for now and would go back to my presentation, especially to the question and answers. So I will now stop the recording and I will put your audio on. So if you want, you can ask any question now to the current theme we had. Just one moment.